Hello, happy Monday. I hope you guys had a good break. Today we are going to get started on Unit 4. It will be a pretty short unit because we don't have a lot of time left between now and the end of the semester. So we're going to talk about work and energy and power, and then we're going to be doing our Rube Goldberg lab. So it's a roller coaster lab more or less, and we'll be kind of combining all of our knowledge for all the forces and work and energy and potential kinetic energy and to kind of come up with some calculations and make some things happen in the lab. So we're going to talk about work today in particular. So at the end of this lesson, you should be able to, if you recognize the difference between work in a scientific sense and just in an ordinary sense, be able to define work, relating it to force and displacement, identify where work is happening, and to calculate that net work done when many forces are being applied to an object. So again, we're just kind of running with this theme of forces and vectors. So we will continue drawing force diagrams, free body diagrams. So there's some stipulations when it comes to work, like what qualifies as work and what does not. So we'll talk about that first. So ordinary definition of work, like if I said I was working all weekend, it's doing something that takes physical or mental effort, right? So like if I was working on lesson plans this weekend, like was I physically moving something around? Probably not. I was sitting at my computer, thinking, right? So we're thinking and we're typing and we're creating things. So that's the ordinary definition of work. But in physics or math, work is to cause a displacement of an object using force. Okay, so those two things have to have happened. You have to cause a displacement, and you have to do that by causing a force or applying a force. So an example would be that Bella lifted a 300-pound stone above her head. Okay, so she's displacing the object using a force that she provided with her body. Some other examples here, if you look at these diagrams on the right-hand side. So if we start at the top, we have this object, this box. So it is being moved over a distance. That is a very plain example. You can also have examples like this man pushing the box up a hill. So, or up an incline, you have obviously different angles that forces can be applied, and we will go through some examples of that. So just as the simple definition, you have this little stick figure guy. Any amount of force being applied that causes the displacement is going to be the definition of work. So because of that, our basic formula for work is W equals FD. So work is force times distance, or the displacement. We're still not getting rid of these other force formulas. So we still know that force is equal to mass times acceleration, or mass times gravity. And then we've used also these trig functions before to solve the forces when angles are involved. So because work is only done when components of a force are parallel to displacement, a force is applied at an angle. If a force is applied at an angle, work is only done in the direction of movement. So the work has to be done parallel to the displacement. So that means that if you are applying work straight across a table, if you're pushing a box across a table, the work being applied, the force being applied is going to be parallel to its displacement. Okay, so because of that, whenever we are doing calculations, if we have angles, which that does happen pretty often, like if you look at this example here on the right-hand side, this man mowing the grass, he's obviously applying a force kind of at an angle there. It doesn't tell us what, but maybe that's a 30-degree angle or a 40-degree angle. Work is only being done in the direction of the movement. Okay, so he's not pushing that lawnmower straight down into the ground. Okay, so work is not happening on the y-axis. Work is only happening on the x-axis. So that's why I made those little notes kind of at the top there. So you would want to use force is mass times gravity times cosine theta. If you are looking for the X component, so in this case, you would use that one. If you were trying to figure out the Y component, so if your displacement was on the y-axis, you would use the one with sine in it. So overall, when you combine all of that, if you look at the bottom of this green equation here, the net work being applied, or the net work produced in a situation, is equal to the net force times the displacement times cosine or sine of theta. So make sure that you keep in mind that that is the net force, okay? And the displacement is going to be the direction, like in the direction of movement. So some other things, just as some reminders here. No work is done on an object if the force is not causing displacement in the direction of the force. So an example of that. We've got Cole, he's carrying his cat across the room. So no work is being done on the cat because the upward force being applied by Cole on the cat is perpendicular to the displacement of the cat. Okay, so in what situation could he cause work to his cat? Well, in this picture up here. So you've got this guy, he has this huge cat. He would be applying work or causing work to happen if he slid the cat across the table, right? So if I just pick something up, like on the very first page, we talked about Bella lifting the 300-pound rock. That's not work unless she is displacing it in another direction, okay? So if Cole is carrying his cat across the room, no work's being done because the upward force is not in the same direction of the motion, right? So the act of picking up his cat, or the act of Bella picking up the 300-pound boulder, moving it upward, she's applying a force upward, the object is moving upward, that is work. But beyond that, it would not be. So in this case, if you were talking about like on a larger scale and you have some equipment, so let's say you had a bulldozer picked up a load of rock. So the act of the bulldozer picking the rock up off of the ground would be a situation where work is done, but the act of that bulldozer moving that rock, like picking it up in its scoop and driving across the ground with it, the driving across the ground is not work being done because the force wasn't applied to the rock in that direction. So units for work is going to be in joules, which is Joules. Also just a capital J if you want to abbreviate it. So that's just another name for a derived unit. In this case, it's newtons times meters. We've seen newtons divided by meters before with like your spring constant and things like that. But in this case, it's newtons times meters, which is just force times distance. So if there are lots of different forces acting on the object, you can find the net work done on the object by first finding the net force. Okay, so everything we did last unit, in unit 3, that was all force work. So don't forget those formulas, don't lose them, because you will still be using these occasionally. So if you have a situation where the net force is not known, but you have other information, you can refer back to unit 3, pull out some of those formulas, find the net force, and then move on to calculating work. So here are some examples. We'll go over example 1's a very, very basic example here. So a CrossFitter lifts a set of weights a vertical distance of 2 meters. If a constant net force of 350 newtons is exerted on the weights, what is the net work done on the weights? So we are just talking about someone lifting them straight up in the air. So that would just be work is force times distance. So we have a force of 350 newtons times a distance of 2 meters. Again, force is always in newtons, and then distance will always be in meters here. That gives us a total amount of work of 700 joules. Another example, you push your cart at the store, like your grocery cart, with a force of 35 newtons at an angle of 25 degrees downward. So you're walking behind it and you're pushing it. You're not pushing it parallel to the ground exactly, right? You're not getting down on the ground and crouching and pushing behind the cart. You're standing, right? So the force is being applied from your arms, your upper body, kind of at a downward angle. So how much work have you done if you push the cart 50 meters? So in this case, we're going to have to figure out our net force and then include some of the trig functions because we do have an angle. So we're going to have the net work is going to be equal to the net force times the displacement times cosine of the angle. So here we're going to set that up. We're at the very bottom here. I don't want to highlight it with my mouse because then that little menu will pop up. You can't see it all. But if you want to focus towards the bottom, I have my free body diagram sort of drawn here. So that's not really a free body diagram, but it is a diagram. I guess I should have drawn a box in the center showing the forces being applied. But here we would have the net force of 35 newtons because this question is giving you the net force. So we'll just have the net force of 35 newtons times the distance of 50 meters times cosine of 25. The reason we're using cosine is because we're pushing the cart horizontally, right? So work has to be parallel to the displacement, right? So if the work, if the cart is moving horizontally across the ground, we want to focus just on the x-axis, not the y-axis, because the cart's not moving in the y-axis. We're not pushing it down into the ground. So for this one, you would just simplify, or not simplify, you would just perform the calculations in your calculator. This one would be 1.6 times 10 to the third joules. Last example here, while playing baseball, you drop the ball and it rolls down a hill at an angle of 30 degrees. If the baseball is 0.15 kilograms and 3.8 joules of work was done by gravity, how far did it roll? So that's another thing to remember, that you can have work done by gravity because gravity is a force, right? Work can be done by any force being applied over a distance. So it could be friction causing work to happen. You could have probably not the normal force, but if you ended up in a situation where the normal force was different than gravity force, you could have work done by normal force. Friction can be done by gravity, so just keep that in mind. So here we know that work is force times distance, and we also know that the net force can be equal to mass times gravity times sine theta. So here we've got sine in here because we're talking about it like rolling down a hill. Most of your questions are going to be a little more specific than this. I guess I can see how this could be taken the other way, where you were trying to find horizontal distance. I don't think I would count either incorrect for that. So if you are reading the questions on the assignment, I'm pretty sure all of them are horizontal, not vertical. This one's just a vertical example. Okay, so we have him rolling down a hill. Like, how far did it roll downward, I guess, because we're talking about gravity. Sorry for the bell. Gravity is being applied downward on the y-axis, so the work in this case has to be applied in the same direction. So if you had a force pushing the ball or pulling the ball, you would have to look at the x-axis, but for this one, you're looking at y. So if we derive our own formula from these two formulas, we can say that work is equal to mass times gravity times sine theta times distance. So we really just have to substitute in our values and solve for that. So we're solving for the distance. How far did it roll? We're going to have the work was 3.8. We knew the mass of the ball was 0.15. We know that gravity is 9.8. And then we had sine 30 because it's rolling at an angle of 30 degrees. And it's sine because gravity is acting on the y-axis. Okay, so our force is acting on the y-axis, so work has to be done on the y-axis. So then we're solving for du displacement. So you can simplify that down and solve for your displacement of 5.2 meters. Okay, so we're going to leave energy for the next one, so I'll go back to this one here. You do have some practice questions to do. I think there are 5 questions and then plus one that has some extra credit opportunity on there. The extra credit one is a little more involved, so you're going to have to find the net force first and then put that into what we know for work. So give those a shot. Let me know if you have any questions, and I will talk to you next time.